Hello everyone, my name is Icey from Imperial College London. I'm going to present our ICRA paper from Red Lab called Mechanical Intelligence for Adaptive Precision Grasp. Here is the outline of this paper, which will include four main parts. First is the background of this paper. Principles of mechanical intelligence have been well developed in underactuated hands for grasping tasks, incorporating elastic and passive elements to generate self-adaptation for dealing with uncertainties. Ma proposed an open-source, low-cost, single-actuator, 3D printed underactuated hand with 4 adaptive fingers. This hand shows the capability of grasping with compliant flexural joints and a differential transmission system by only using one motor. For robotic hands, there are two major types of grasps, power grasps and precision grasps. The power grasps are also called cage grasps. The contact points can be distributed on all finger phalanges. Therefore, power grasps are more tolerant to dynamic manipulation due to large contact areas. The precision grasp is associated with the handling of objects between the fingertips, also called the pinch grasp. The ability of underactuated hands to perform precision grasps on objects is very limited. Because the precision grasp is normally unstable, due to a limited number of contact points, two-fingered grippers struggle to keep the object with additional dynamic forces from the robot arm. Recently, soft robots inspired by tendrils of plants have been developed for holding objects. Hu and Icey 3D printed helical pneumatic actuators and used them as fingers for grasping objects. For helical pneumatic actuator finger can either bend like a normal finger to grasp the object or twine around the testing objects. The characteristic provides high adaptation to the shape of the object and secure grasps. However, this soft helical motion is complicated to model. The grasping control is not straightforward compared to rigid structure. Taking this as inspiration, in this paper, a rigid helical structure is proposed, which is based on parallel manipulator to perform helical power grasps with 3 fingers positioned in 3 orthogonal planes. With this hand structure, the finger can coil around the objects. Moreover, with the differential tendon design, the helical hand can perform precision grasps on different objects and self-adapt to the object shape by only actuating one servo motor. This is the full CAD model of the helical hand, which is designed based on the topology of this underactuated hand object system. In order to actuate the proximal links in 3 different orientations by using only one motor, a specially arranged and designed bevel gear transmission system was used. The distal links are driven by a single motor via a tendon with a differential system in it. Here is the tendon routing of the hand. The tendon starts from the back of the distal link, goes around the proximal joint, and finishes at the differential plate. Given this routing method, those distal links are compliant and adaptive to the proximal links. As there is a differential system connected to the distal links have compliant and adaptive characteristics when just controlling the proximal links at a constant speed when grasping large regular objects. For small and irregular objects, the additional actuator for the differential plate can be set at a constant speed to provide large compliant adaptability and strong grasp. In order to evaluate the grasping performance of the helical hand, 3 individual tests were conducted, which including the grasping capability, the grasping tolerance of the position arrows, and the pinch grasping strength. The first experiment shows the self-adaptive precision grasp of helical hand by using YCB test objects. The grasping capabilities of the helical hand was also quantified by evaluating the hand according to the gripper assessment protocol described by Carly. During the test, the helical hand was attached to the UR5 and picked up each object from a smooth workbench. For each object, the test started by finding a grasping strategy which persistently grasped the object with the target position. The hand was then scored based on its performance to grasp each object from a workbench from the target position and move by 10 mm in XYZ direction without adjusting the grasping strategy. The table shows the score of the testing objects. I will discuss it later. The hand is also capable to transfer the position grasp to power grasp under extrinsic force. The second experiment tests the hand tolerance of positioning arrows by moving objects offset in the XYZ direction along the diagonal axis. In general, a large grasping region makes the hand more tolerant to the positioning arrows. This grasping region is defined as the grasping workspace of the hand. The kinematic analysis of the helical hand and the static modeling of object configuration workspace have been analyzed in the paper for references. 3 markers were positioned at each proximal joint to define the coordinate frame of the gripper. A 15 mm triangular object with tracking markers was grasped by the gripper at several positions. The object was held until all the fingertips were in contact with the object for each attempt grasp. Once the gripper successfully grasped the object, the motion tracking cameras recorded the position of the object and the orientation of the object was post-processed in MATLAB. The last test was to measure the grasping strength of the helical hand. The compression load cells are installed in the testing object to detect the grasping forces. To test the grasping strength, the hand was placed on a desk and the object was suspended right above the hand. The test was terminated when the hand grasped the object 10 times at maximum torque. The mean and standard deviation of the grasping force are reported. The resultant precision grasping force of the helical hand is around 10.8 Newton with a standard deviation of 0.33. The ear-open hand Model T and Model T42 have similar grasp forces around 11.5 newtons and 9.6 newtons respectively. However, those are the power grasp force, which normally larger than the pinch force, especially for under-actuated hands. The overall score of the YCB tests of the helical hand is 318 out of 400. However, the helical hand has deficiency on small and flat objects. Nevertheless, the precision grasp capability of the hand is satisfied, and the helical power grasp delivers more support on the grasping object due to the large contact surfaces. In summary, the mechanical intelligence principle and the differential system have been proved by this introduced prototype for self-adaptive precision grasping and helical power grasp. However, these prototypes still have some aspects that can be improved. Maintaining stable and robust contact conditions during the position grasp and under dynamic force remains a considerable challenge. The passive rotary fingertip attachment design can be improved by minimizing the pinch force loss and increase the stability. By controlling both motor in a certain way, the grasped object can move in a helical motion. Moreover, each proximal finger could be actuated separately to have different in-hand manipulation behaviors. It would be useful to extend the grasping ability and the potential applications as well. And thank you for listening. Bye.